So it's a great pleasure to be here again. And I used 3 seconds to switch laptops because I was kind of concerned after Ben's talk. So let's hope this one will work better. So I'll tell you a little bit today about Datto and what we do. So first, a few notes about myself. I was a PhD student at the Hebrew University in the Distributed System Lab under Danny Dolev, Professor Dolev. And I did a postdoc at Carnegie Mellon University, where I started to work on a GraphLab open source project, which later turned into a company named Datto. About Datto, we are a Seattle-based company. We have around 50 people worldwide, and we have a small office, a small subsidiary in Israel, near Jerusalem. So we are promoting data science also on this side of the world. So just to phrase what kind of the context of what we are doing, we have got to the insights that companies are, they want to store the data. This is kind of a pretty solved problems. We all are familiar with databases. Whenever you want to store data, it's kind of a solved issue. And later companies are not only they would like to save the data, they want to be able to query, to have some kind of dashboards. So this is in current years, companies like Tableau are very successful making this kind of visual interaction dashboard. But now the things that are way more interesting is not only storing the data and viewing it, but also trying to understand the data better and making prediction what will happen next. So that's also trying to understand the data you have and not just to store and view it. So this is the area of application we work on. And there are many types of different applications. I will show some of them now, and some of them in my next talk that will be focused on recommenders that will be in 2:30. So anyone interested in recommenders is welcome to get a more detailed use case. So there are many different types of predictive applications one can generate using machine learning, and there are many of them. So some examples are recommenders, fraud detection, social graph analysis. And I want to show just a few examples here. So whenever we start to talk about intelligent application, we always start from data. Whenever a company comes to us and tells us we are an aerospace company, we need help about devising our future machine learning infrastructure, we always ask them, do you have data? Because if they don't have data, we tell them, first collect your data and come back to us in 6 months, because we cannot start without this is the basis of everything related to machine learning. And some companies are not familiar with this. So there are different types of data we can handle, and there are a rich set of the differences like image data, text data, graph data, tabular data, and also time series data. So, and each one has their own specific characteristics. So I want to show a quick demo of what is a predictive application. And let's hope the internet will work. Yeah. So this is a very cool area which is called deep learning that was mentioned by Ben regarding working with images. And the task here is try to classify the image, to say what's the label inside the image. So here I have a predictive server which runs in US West Coast in Amazon. And what I'm doing, I'm basically sending an image to the server, and in a real time, I'm getting the score of what's inside the image. So in this case, we predicted in around 90% certainty that this is a balloon, and indeed, the true label is a balloon. Of course, there are different types of images, so I can try another one. This is kind of easier even, indigo bunting, it's a kind of a bird. This area is very exciting to people because only a year or two ago, the humans have become the humans are less smart than the computer. In other words, the computers are more proficient in identifying images. And now the state of the art is around 54% of correctly guessing what's inside the image or labeling what's inside the image. And the task is rather difficult because you have 1,000 potential labels in this data set, which is called ImageNet, which means that there are a lot of types of birds and dogs and products and so on, and it's very hard for a human expert to actually know all the labels. So this is one example of a predictive application using images, and I want to show you another example of predictive application, this time using text. So this is a different type of a data set. This is a data set from Mexican restaurants in San Francisco. And what I can do, I can search about keywords that appear in user reviews on this data set. So kind of an interesting example I found some time ago is when you search for the keyword fat, fat has a relatively negative connotation. So whenever I say fat, I think this is a fat food, probably not that great. But I wanted to check to see if we can score the sentiments of what people are talking about in the context of fat regarding certain restaurants. So what I'm having here, I have a list of restaurants and I have different scores. The scores are sentiment scores to see how people refer to fat in this restaurant. And let me show you one example in detail. So this is a Tommy's restaurant. I'm opening it. Again, all the back end runs in the cloud. And then I will show you in a few minutes how this actually works. So I'll start with this, and I'm not sure you can see all those sentences in the back. But whenever we look at human data, the results are rather kind of crazy because humans are generally crazy. So I'll skip the first one. But the second one I like, so I get a combination plates because I'm fat and I like to eat. So that's a very good sentiment. Also, this place I gave fat tips. So that was kind of nice. I was happy. And they had a fat tequila selection, which is also very good. So all of those are positive sentiments from the context of the sentences. From the other hand, of course, we have also negative sentences with the word fat. So for example, if you're into lousy food and fast-paced white chicks, this place might be for you. The room was so crowded to the point that if we yawned, we could have given our neighbors a fat lip or black eye. So that's also a negative sentiment, most likely. And this place can suck a big fat one, and so on. So everything has the keyword fat, but in different connotations, and the application here is trying to understand what the writer means and what is the actual feeling about this place. Okay, so those were two quick examples about things we can do, cool things with the predictive application. And if we can look a little about how the working model typically looks like. So we start with some data set. As I said, no data, we are out of jobs. The second thing, we would like to clean the data, make some transformation, join data from multiple sources and so on, prepare features. And then we would like to model the data in order to understand what's going on inside. But that's not the end of the task, because actually we need also to have some predictive capabilities. As I showed you with the demos, we would like to be able for a user to interact with our applications and get some interesting insights from the data in real time. So this is the deployment part. And this is an iterative process, because once you deploy, you may find you like to improve the data, improve the models or get more data and so on. So what are the ingredients of the serving side? The serving side is the kind of the interesting side, which is a bit ignored, because typically as researchers for machine learning, we are mainly worried about which algorithm works the best, what's the performance, what's the running time, and so on. And in many cases, we ignore how it can be done to actually serve this model in production and in real time. And when I say real time, we typically mean to serving side between 5 to 10 milliseconds. That's the requirement of the major applications we are supporting. So we would like, from the one hand, the servers to be responsive, to be quickly return the results quickly to the user. From the other hand, we would like the service to be adaptive, which means that models constantly change, users change the preferences, things change, news come in, and so on. And the third thing, that it will be easy to manage a lot of models together and track their performance. And for that, I want to dive into my last demo for now, which is the serving side, how it looks if we look at it a bit more carefully. So let me jump again to my last demo. And this is an example of a book recommender, but I'll show you in a bit more detail the serving side. Okay, a new version of Java. I don't care. Let me increase a bit, maybe, I don't know. I hope you can see it well in the back. But what we have in general, as I showed you, we have some predictive application. The predictive application are interacting with a few predictive servers. The way it works, it's kind of a query response type of interaction, where we have a load balancer in order to scale to a lot of nodes, or if one node fails, we would still like to overcome the computation. So I'm going to start with some random item, and when I'm picking some book, I get some similar items to that book. So this is a recommender model which is now running live. And what I can do, I can click on any other book, and then I get some other books that are kind of similar to it, and this is based on the recommender model. So if we dive a little more deeper into how this is constructed, so basically we have now a server which runs now on Amazon EC2 West Coast, and we are sending a query. The query is a JSON object where we send to the server, and then we get the response of what are the recommended items based on the initial request. So this is how the interface looks like. But if we'd like to dive in a little more, we first have some tools for creating this server. So this is a very easy task. We have a Python interface. In 2 lines of code, you can actually generate a server and deploy it on EC2. If the server is already deployed, you can connect to it. The next thing you can do, you can have a lot of models constructed in any Python package. Like in this case, the model was constructed using our tool GraphLab Create. And here we wrap the model and then add it. Basically, we name it and then commit it to the server. Once the model is committed, the server can start serving requests. The tools to connect with the servers, you could write Python code, but also you can connect it to JavaScript or any other programming language that supports RESTful API. In this case, curl. So it's very easy to interact with the server. And we have also tools for providing feedback to the server, so the server could adapt the models while running. Once you have a model in production, you're also very interested in understanding how this model works. And for that, we have tools to track the model, to see how the model is functioning. And we have also tools for experimenting with several models. So if you have a few models, you're not sure which model is the best, you can spin up a few models in production and then have some smart policies in order to deciding which models behave the best. And we have also adaptive models that can learn from the client behavior and improve on the fly the way the model works. The last thing, there are a lot of things that are more gory technical details about versioning, logging, auditing, permissions, reviewing operation logs, and everything is supported by our system. So let's get back to my slides. Okay, so in the basis, in the Coursera system, we have our own engine for a machine learning predictive application, which is called GraphLab Create. So I want to discuss very briefly what's the main concepts and layers of our engine. So we are based on an open source project, which is called S-Frame. It's a pip repository, so you can install it, and you don't have to sign up or anything. It's completely free BSD license. On top of our engine, we have data structures that allow you to store different types and work with different types of data. The main data types we found to be effective here are S-Frame, which are tabular data structure like data frame. We have also scalable graph, which is a special data structure for handling graph data. And we have time series data structures, which allowed you to query and work with time series. On top of our engine, we have machine learning toolkits, which are implemented with a Python interface. And they are free for academic usage, but they cost some licensing fees. And of course, we have also our predictive servers, which is the server component, which wraps up the model with RESTful API and you can deploy them either on-premise or in the cloud. We run on different types of environments. We run also on Hadoop. We are certified for Hortonworks and Cloudera, and we also support GPUs. We can run on Windows, Linux, and Mac, so we run almost everywhere, and we also have an interface through PySpark, so you can also, if you're working with Spark, it's easy to import us and work with us. So a few words about why actually use us. So we have much superior performance for very large data sets versus traditional tool. And one of the main reasons is that we have efficient representation on disk, which is compressed column store based. So as you can see in this example, we are about 20 times more compressed than Pandas, which is equivalent Python package for data engineering. And once we have less, we require less disk space, we can actually read faster from disk. So effectively, if you compare to Pandas, when we work with flash drive, we are only twice slower. And when we work with the traditional hard drive, we are only 5 times slower versus equivalent software. But from the other hand, we can scale to much larger data sets. So I want to show a bit of the performance results. So this is a quick comparison to scikit-learn. The task here is linear regression on a fly data set. Anyone interested can download it and play it on your own if you don't believe us or you want to try it out. And what we have here, the y-axis is the runtime, as lower as the better. So we run about 50 times faster than scikit-learn. But the problem with scikit-learn is when it gets to around 90,000 rows, the machine simply runs out of memory because the problem gets bigger and bigger. And then you're dead. So you always need to sample the data into small parts and then do some modeling. While with us, you can continue, and even if the file is 10 terabyte and you have large enough disk or network file system, then you're pretty good to go. Another quick performance comparison to another package which is kind of popular, which is H2O. So this is another task of deep learning, digit recognition benchmark. And here you need actually 10 machines of H2O with 10 hours of computation to what we can obtain with a single machine in 4 minutes. So that's again about 2 orders of magnitude faster, and furthermore, we also get better accuracy in the computation. One last performance example regarding graph analytics, and this is a comparison to Spark GraphX. So here we are about 3 times faster than GraphX, but what's interesting is that it's mandatory that you will have at least 16 machines for this computation because you need to load the problem into memory. And in our case, we can simply run from disk. So it's also way faster and you save a lot of computation resources. And this is the realized one regarding much larger graph. That's the larger web graph available today with 130 billion edges and 4 billion nodes. We can work on a single machine. It takes 9 minutes per iteration of PageRank, which is an algorithm for ranking the importance of graph nodes. We have also a distributed version that runs on 16 machines, about 10 times faster. The problem with Spark GraphX here is that you cannot load into the problem into memory. The problem is too big, and we had a customer that tried with 300 machines and get a lot of memory errors. So these kind of problems are rather difficult to solve using Spark. One last note about our customers. We are growing in industry, and as you can see, we have a lot of brand name customers, and we have some of them here also, and some of them will give talks today. And one last note, we have a popular course on Coursera, which you can take for free. It's a data science course. We have already closed nearing to 50,000 students already. It's jointly with the University of Washington. It's a certification composed of 6 parts, so you can choose which parts to take, which are more interesting for you, or everything. And once you do it, you get a free license for our software, so you can do all the homework. And the teacher is the CEO of our company, who is a professor at University of Washington, Carlos Gestrin. Okay, so this finalizes my talk. Thanks a lot.